All right, everyone, welcome to our second video in our series of 4 on the calculus that you'll need to understand to do well in intermediate microeconomic theory. And last set of slides, we did functions and the intuition of what derivatives are. But now we need to get more into the nitty-gritty about how to take the derivatives of functions. So what I'm going to cover in this slide is rules for calculating derivatives 1. And I'll save some rules for next slides as well as partial derivatives, and then eventually I'll get to maximum and minimums and finding the extreme of functions. And I've got more memes in this one, so solving for the derivative via the formal definition, ain't nobody got time for that. And so we're going to be using the derivative rules to get our derivatives. And I'm sorry about the memes. I didn't feel like I needed to make any, so they're really old meme formats. Uh, this is kind of a nice blast from the past. So anyway, we're going to just talk about rules for finding derivatives. So we need to focus on finding the derivative functions of total functions. So if you took calculus, you might have been introduced to this as the total function is the position function, and the first derivative is velocity. And then you'd have the second derivative of the derivative of the first derivative, which would be called the second derivative, meaning the acceleration of an object. In economics, the most common total functions that we'll be using describe utility, revenue, and costs. And so taking the derivative of these total functions yield marginal utility, marginal revenue, and marginal costs. And so using the rules ahead, we'll be able to find the derivatives of total functions without having to like make h go to 0 at every single point on a curve, and not have to use that limit formula. And so we can get this marginal utility as the first derivative just from the function of the total utility. And so I'll come back to this later in this set of slides. And so we've got rules for derivatives, and there's lots of rules for derivatives that you need to keep straight. And so I'm going to cover 7.5 rules in these slides, and I'm going to do the first 4 in this set of slides. And just so you know, this list is not exhaustive, but it covers the ones that you're most likely to come across in this class. And so we got Thanos powering up with all his rules of derivatives. And the first one, which I didn't mention, which is called the constant rule for a reason. The constant rule is the most simple one out there. If there's a graph of a constant function, then the slope is 0 everywhere. So when it's time to differentiate a constant, you have evil Patrick from SpongeBob, and you'll see why. So let's say we have y equal to c, which is just some constant number, i.e. it could be c could be 6, it could be 241, it could be pi, it could be 11/4. What's most important about it is there's no x in there. So we know that the graph of it just looks like this. And so this is a constant function of y equals 3. And y doesn't depend at all on x. It's just 3 everywhere. And so you'll notice that our slope formulas rise over run. At every point on this function, rise is 0. So for every single pair of x's, slope is 0 everywhere. And so the constant function's derivative is going to be just this graph here, which is the slope of y here in this upper total function is 0 everywhere. And so hopefully this helps to get the wheels turning on what derivatives are actually meaning, is that it's just literally the slope at every single point up here, which is 0. So this line's not sloping at all, so the value of this is 0 everywhere. And so if you have y equals some constant, then the derivative of y is going to be 0. All right, and so this is all the things that I just said, and so you should really make sure that you understand that and what we're kind of trying to say, and contrast that with the parabola from the last set of slides. Okay, now we need to do the addition rule. And so if a function can be written f of x equals g of x plus h of x, then we know the derivative of f of x is the derivative of g of x plus the derivative of h of x. All right, so now I doubt few of you look at, say, some example function. I'm going to use y equals 2 times x plus 3 over x and say, sweet, f of x equals g of x plus h of x. But the reason the notation looks like that is because it needs to be generalizable to many different types of functions. And so that's why it's written that way. But I'm going to walk through a very basic example. And so it's really not as intimidating as it kind of looks. What it's just saying is that the derivative of f of x, or d of y, d of x, is just equal to the derivative of 2 of x plus the derivative of 3 of x. And so we can just add the derivatives of either one of them, of both of the different functions together, or on either side of the addition term together, and we'll get the correct derivative for y. And so that's a pretty general rule that will come in handy in a lot of different cases. And so we need more rules to figure out exactly what the derivative of 2 of x and the derivative of 3 over x are, or any other possible potential g of x or h of x. But for now, at least we know how to deal with adding two terms or two different functions. Okay, so I need to do a quick notation definition aside. So the book uses d of f of x dx to mean the derivative of f of x. And this is technically formally correct, but it's pretty notationally cumbersome. So I'm going to simplify the notation in these slides in some places to make it a little bit easier for myself. So you might have noticed in the last slide that I just freely substituted f of x for y, and I kind of went over that in functions and derivative slides, but I wanted to make it again explicit for you. So when you have a function and you plug x into f of x, then f of x and y are equivalent, given that it's a function. And so it passes a vertical line test. And so that's how we know that x, uh, f of x and y are equivalent. So you might have seen these tables before, and you can see that when we plug -2 into our function, it gives us -7, and we can see that f of x and y are equivalent. So if you do 2 times -2 and subtract 3, then you get -7, and so we know f of x and y are equivalent, and the same for any of those x's. Because we know that 2x minus 3 is a function, it passes a vertical line test. Whew. All right, so f of x equals y. Now what? Now I want to have some shorthand for f of x, for the derivative of f of x or y. And so I'm going to use f prime of x or y prime to represent the first derivative of f of x or y. And so this is going to be pronounced f prime of x or y prime, respectively. And right now we can shorten this up because we're dealing with functions of one variable only so far. And so putting it all together, one from last slide, this, I can rewrite this with less of the dx's by just saying, okay, that's also equal to y prime equals 2 prime x, or 2 times x prime plus 3 over x prime. All right, so we're moving right along here. Now we need to deal with a function where the terms are multiplied together. And so the book has it, if a function can be written f of x equals g of x times h of x, then the derivative is f prime of x equals g prime of x h of x plus g of x times h prime of x. All right, so and you can notice that you can switch these around because it's an addition sign. So, but what I say is the product rule is f prime of g, or g prime h plus g h prime. And so our example function is 2 times, now we change our example function to 2 times x times 3 over x, which is a little bit more involved. Then we know that from the product rule, y prime equals the derivative of 2 times x times 3 over x, not derivative, for lack of a better word at all. And then plus 2 times x, not the derivative form, and then times 3 over x prime. And so this h of x is 3 over x. We took the prime in the second side for h of x, and we took the prime of g over x on the first side, and then multiplied it by the other function just without needing to take its derivative first. And so recall the little apostrophe symbol stands for derivative or prime. The term on the left means we need to multiply the derivative of 2 times x by just 3 over x. And the term on the right means we need to multiply 2 times x times the derivative of 3 over x. And that will give us the derivative of y equals 2 times x times 3 over x. All right, so now we have our product rule. And we're going to get into how to actually take the derivative of 2 times x and 3 over x. Hopefully you're curious about that by now. Well, if not, well, too bad, because here they come. Well, just one. So our function is just, let's say we don't have the 3 over x at this point. We just have f of x equals 2 times x. All right. Well, then the derivative of f prime of x is just 2. And I'm sure probably most of you remember that from business calculus if you've taken it already, which you probably have. And it was really that easy, and I'm not messing with you, right? But this is really only a specific example of a more general power rule that you're going to need to also remember it's going to be very important for you to remember. So this is a specific example. It is only really slightly harder than this. I and many others find this to be basically the easiest rule that you should take advantage of whenever possible. All right, so if a function can be written y equals a times x to the b power, in which a and b are constants, then we know the derivative is just a times b. This is what you did in the last function. You just said um, x squared. Well, you multiplied, or 2 times x, you just multiplied 2 times x to the 1. So 2 times 1 is 1 or 2, and then you subtracted 1 off of b, or off of 1, and that was x to the 0, which equals 1, and then you were just left with 2. And so that's the derivative, is just a times b times x to the b minus 1. And so an example like that I showed you that we did in like kind of the last slide is y equals 2 times x equals 2 times x to the first. We usually don't write x to the first. It's just kind of awkward. It's already implied. However, it's useful to make it explicit here so we can see how the power rule works. We say, all right, well, y prime equals 2 times 1 times x to the 1 minus 1, which equals 2 times x to the 0. And so anything to the 0th power equals 1. And so we have y prime equals 2 times 1 equals 2. Simple. I'm pretty sure that you probably all knew that, but hopefully expanding it a little bit helped for you to see the machinery kind of going on underneath. And now 2 more power rules examples, and so this is pretty important. So let's first find the derivative of y equals 6 times x to the 4th plus 2 times x to the 9th. Just make it a little more involved. First, the addition rule means that we can just go ahead and take the derivative of this and add it to the derivative of this, and we'll have the derivative of the whole thing. And so let's work on the left term first, that is the 6 times x to the 4th derivative. Well, what we need to do is we need to take this 4 down and multiply it times 6, and then we need to take 4 minus 1, as the power rule states, as you can kind of see up here, and we can see that 6 times x to the 4th derivative equals 24 times x to the 3rd after simplifying. And then we'll work on the right term a little bit, the 2 times x to the 9th derivative. And we can see that we need to take the 9 down and multiply it by 2, and then subtract 1 from the exponent, which is 9. And we have 18 times x to the 8th. And then we can put it all together and say that, all right, the derivative of y equals 6 to the x to the 6 times x to the 4th plus 2x to the 9th equals 24 times x to the 3rd plus 18 times x to the 8th. And this is a fine answer for the derivative of the first function. And so we could simplify, but the problem doesn't ask. You can see that there's 6 times x to the 3rd, and we can factor that out of both terms. We don't need to do that at this point, unless the question asks you to do more on top of that. All right, so the next thing we need to do is find the derivative of u equals q to the 0.4 power. This is a function from slide 2 and from the other slides. And so we see that u prime equals 0.4 times q to the 0.4 minus 1, and we have u prime equals 0.4 times q to the negative 0.6 power. This is a perfectly acceptable answer for the derivative of u equals q to the 0.4. But I know everyone gets kind of scared by negative exponents at your kind of stage of your career, and it's really not that scary. It's just u prime equals 0.4 times 1 over q to the 0.6. So if we want to get rid of the negative, then we can just send it to the denominator of a fraction, and then we can even simplify this, and we get u prime equals 0.4 over q to the 0.6, and that's just the derivative. And so we have just found our first marginal utility function from our total utility function. So we're on our way. And then one thing I want to do real quick is show you how this is consistent with the law of diminishing marginal utility. So in general, the math way to say it is consuming the qth unit should give less utility than the qth plus n unit, where n is greater than 0. Or kind of a specific example in English is consuming the 10th unit should yield, that should say more, should yield more utility than the 25th unit. All right, so u prime of evaluated at the 10th unit equals 0.1. U prime evaluated at the 25th unit equals 0.057. And so we see that the utility of the 10th unit, the marginal utility of the 10th unit is greater than the marginal utility of the 25th unit. And we have the law of diminishing marginal utility is satisfied everywhere. It's great. And then alternatively, we can just see from this function that it's negatively sloped everywhere, which is why the marginal utility of the 10th unit is greater than the marginal utility of the 25th unit. Pretty neat. And so the law of diminishing marginal utility is satisfied for this function. All right, now the quotient rule. If a function can be written as f of x equals g of x over h of x, then the derivative is f prime of x equals g prime of x h of x minus g prime, or g of x h prime of x over h of x times h of x. And so from this derivative over here, the easiest way to remember this rule is low d high minus high d low over low low. I still say this to myself every time I need to take the derivative of a quotient, and I always forget it. This is my least favorite derivative rule. It's really easy to mess up if you don't get the order right, and it usually ends up with lots of terms, and I really like avoiding it if possible. And I'll show you a way to avoid this rule. It just involves negative exponents. So get used to negative exponents if you can. And so low d high, low is just, here's low, the d high minus high d low over low low, low squared. Anyway, that's the quotient rule song. Here's an example for you. I'll try to keep it as simple as possible. Like, remember we just had 3 over x in our kind of toy example so far. Then the derivative f prime of x equals x times the derivative of 3 minus 3 times the derivative of x over x times x. And the derivative of 3 over x is negative 3 over x squared. Okay. So now let's put it all together. Remember, we had this toy function, y equals 2 times x times 3 over x. First, we can use the product rule like we saw earlier to expand it into this. And then we just need to evaluate all the derivatives and possibly simplify if we want. All right, so first we're going to use the power rule on the left term's derivative. That's the 2 prime x times 3 over x. And so the derivative of 2 times x is just 2, like you guys already know, and then times 3 over x. And then we have this right term that we need to deal with. And so I simplified this here, and then we still have the right term. And we have, from the quotient rule from slide 13, we know that 2 times x times negative 3 over x squared is just the derivative of 3 over x is just negative 3 over x squared. Go back to slide 13 if you want to see it again. And then we have y prime equals, after simplifying, 6x plus negative 6x over x squared. All right, this is kind of jarring, but simplifying this algebraically gives us y prime equals 6 over x minus 6 over x, which just equals 0. All right, so that was a lot of work just to get to y prime equals 0. I didn't plan that, and almost always that won't be the case. But it's kind of interesting to see that we can do other things before we take derivatives and get the same answer. So as long as it's mathematically correct, we should get the same answer. So let's look at another way to do this. We can go from 2 to 3 on slide 14 because we had already done the quotient rule on 3 over x. But if we hadn't done 3 already, if we hadn't done the quotient rule on 3 over x, then equation 3 would have looked like this from the last slide, which is kind of a lot of terms to look at. So Instead, we could just rewrite 3 over x using algebra as 3 times x to the negative first, negative exponent, and then we could just use the power rule, which you guys are very probably comfortable with. And so we'll just use the power rule on this instead of using the quotient rule on that, and we can say the same thing. So y prime equals 6 over x plus 2 times x times negative 3 over x squared, which just, as we saw in the last slide, simplifies to 0. And then there's even another way to skin this cat. So back to our original, or not original, but after we rewrote the negative exponent like this, um, calculus is like sort of hard. At least it's more unfamiliar to most of you. Algebra should be a little less hard. And so you can use it to your advantage in this case. The when appropriate is the hard part and requires practice. So this would be actually a good place to use algebra. We could just combine terms before we did any calculus, and we could have y equals 6x over 6, or x, which is just 6. So now we have y equals 6, and instead of needing the product rule, the quotient rule, the power rule, we can just use the constant rule, which was Patrick, as I showed you earlier, and we'd have the exact same solution with a lot less calculus because the derivative of a constant is 0, always. Now, it's almost never this convenient. You're going to need the rules in this class, but I just thought it would be a fun way to show you there's more than one way to skin a cat. And so here are the same extra resources I showed you in the last slide. Feel free to dig in if you think you want some more mathematically precise reasoning or some other background from Khan Academy or something like that. All right, so thank you for hanging with me through derivative rules 1. And the next set of slides, we'll do derivative rules 2 and start talking about partial derivatives. Thank you.